Dear colleagues, speakers, and participants, it's a real pleasure to welcome you today. My name is David Morgado. I'm a Senior Energy Specialist at the Asian Development Bank. I'm your chair for this thematic track on innovative low-carbon technologies, and I sincerely hope you've been enjoying the program we've put together for you over the last 3 days. Today is our final session of this thematic track, and the topic is on embedding climate resilient and adaptation strategies in energy systems. The aim of this session is to talk about how we can enhance energy systems to be more resilient to extreme events and climate change. Many of you might be asking, what is climate resilience? So climate resilience is the ability to anticipate, to absorb, accommodate, and recover from adverse climate impacts. Great, but why is it important? Well, energy security is, as many of you know, energy security is essential for any country, particularly as we become increasingly electrified and are becoming ever more dependent on energy for many of our daily activities. Climate change will have a detrimental impact on all parts of the energy system today and in the future. This includes floods, droughts, rising sea levels, heat and cold waves, wildfires, extreme weather events, and many more. Therefore, it's critical that we develop policies and technologies to build a resilient energy system in both generation and transmission and distribution, and even on the demand side, as we'll hear today. A resilient energy system will deliver significant cost savings, even if the initial investment might be higher than usual. We have a very interesting session today and great speakers covering a range of real-life examples of different technologies and approaches that will help our energy system become more resilient, including in developing countries. We've got about 1 hour and 20 minutes, with the first 30 minutes with 3 presentations, and then the remaining time for panel discussion and questions and answers from the audience. I really invite the audience to be very active and collaborate with us, and so that we can make it even more interesting. I kindly ask speakers to keep to the time allotted so we can ensure we have sufficient time for discussion. To start, it's my pleasure to invite our first speaker, Michael Carroll, who's the CEO of Elias Altas Corporation, where he's developing reliable renewable energy systems. He'll be talking a bit about reliable renewable energy services and how it survives a typhoon and is the only power for kilometers. Michael Carroll, the floor is yours, please. Thank you.
Great, thank you very much. Hello, and thank you for your time. I'd like to quickly tell you about our team and what we're doing. Elias Altas is made up of an engineering and energy professionals that have created and completed hundreds of millions of dollars of energy projects around the world. With that experience, we've utilized our decades of contacts to create an ideal company that makes the most impact for renewable energy technology since the solar panel. Another key part of our team is our manufacturing partner, Hunting Energy, who's been a constant support for us with engineering and resources, and actually built the units we'll be talking about here today. I'd also like to thank our local Philippine distribution partner, One Renewable, whose support has made this project possible. Their team is actively building a pipeline of commercial projects and identifying sites for local emergency power stations literally as we speak. I hope that you too will be able to join and support us on this venture, which literally will help change the world for the better. Here's a quick overview of the technology and what we're talking about. Right now, there are terawatts of power flowing down rivers and streams that are not being utilized. But more importantly, there are hundreds of gigawatts of power flowing through man-made structures that aren't being utilized. We capture this energy through the Helios power wheel, which comes in sizes from 40 watts up to 10 kilowatts. The units are convenient, easy to install. They require little to no civil works. They can be integrated with solar, batteries, or other technologies. We typically generate a minimum of 3 times the power of similarly rated other renewable technologies. What's unique about our units is we can operate in much slower water than normal. We've got a patented design of how we can actually generate Typically, you get about 35 to 40% of the energy out of one of these wheels, and we operate generally between 65 and 70% of the energy, which is a huge advantage. We can produce power from very thin water flows, which is also unique to our system, which means we've got exponentially more places that you can put these units. They're also suspended on a pendulum, so they can rise and fall with changing water levels. They can allow debris passage, aquatic passage, and we actually can raise and lower the units remotely or locally. We have well over 100,000 hours of operation with our units. We've been running multiple units for more than 5 years now, and we've just been improving on that design to what we have today. And so what we have is in December last year, Typhoon Odette hit the Philippines, and we had actually powered up a village called Balingasag in the Philippines in northern Mindanao, and we've been powering that village for almost 3 years now. We've been updating units as we've been doing our development in there, and our latest unit was installed just before the typhoon hit. It was a Category 5 typhoon, which devastated the country and particularly this area of the Philippines. When the typhoon was coming, the villagers had the unit in the water. They were able to have power up till the end. When they went and decided to seek shelter, they raised the unit up out of the water, so it was safe. They sheltered for about 48 hours. And when the storm died down, they came back. They really hadn't eaten anything. The kids hadn't eaten anything. And it was around 10:30 at night, so it was dark. When they got there, they were able to lower the wheel into the water, and they had lights and power, so they were able to cook and being able to charge devices.
Hi. So it seems we've got a slight
private link.
Okay, Michael is back. Sorry, Michael, we lost you just for about 10 seconds. So can you go back to the previous slide? So,
okay.
But you're live now, so we can see you again. Thank you, Michael.
Okay, great. So the villagers, I'm not sure exactly where I left off, but they were basically sheltered for 48 hours. They came back to the village. They hadn't eaten, the kids hadn't eaten. It was 10:30 at night. They lowered the wheel into the water flow. This instantly turned on power, so they had lights and they were able to cook and see what they were doing, charge their devices, and then get connected with the world. This QR code, I'll give you a minute here, but this actually will take you to a private page on our website. There is a rough video of a report from the villagers themselves telling their story, so you can see that. And there's also a video of the exact unit 2 months after the typhoon hit. And you can see the unit in operation. Our Lito Morales, our electrical engineer, is demonstrating how the unit can be raised and lowered at a push of a button. And we're also setting this up so it can be done remotely as well. So moving on. So what occurred after the hurricane or the typhoon came through, all of the roads were washed out from the rain. So once the diesel generators ran out of fuel, they couldn't get trucks or transport there to fuel up the generators. The grid was out for over a month in the area. So what happened was everybody in the neighboring villages for kilometers around came to the site to charge their devices, charge their phones so they can get in touch with their loved ones and be in contact and connection. So it was actually pretty emotional for all of us when we learned about all this, because we knew that the typhoon hit, we knew it hit right in the area we were at, and we weren't obviously hearing anything for quite some time ourselves as well. So when we were able to get in communication with them, we were just ecstatic to find out that everybody was okay in the village and the area, but that too, that the system worked so well and was such a valuable help to everybody there. So it was a great moment for us. And so what really helps with the system too is that it's a non-blocking system. So we're able to allow debris to pass through. So you can imagine after the typhoon came, the waters were extremely high still. So there was a lot of energy, a lot of debris, a lot of things coming down the canal from all of the water flow and everything else. And all that was able to pass underneath or through the unit. And it operated without issue and was able to handle all of that. So that was a really critical part of the technology and what made it work and serviceable through this. One other part, the unit itself has a synchronous generator. So the only moving parts are the bearings of the generator. So there is very little to break or go wrong with it as well. So we purposely designed this to be able to handle situations like this. And these units are truly designed to last 30 plus years. And obviously made to handle situations like this. The units can also be connected into what we call hydro farms. So they can be in series down wider water flows, in parallel down water flows, or in series. So you can expand on systems. So you can start out with one wheel and increase to multiple wheels. We've actually done surveys of sites which could handle over 10 megawatts of power. And then again, with the microgrids, which we've shown with this village for the last 3 years, we can integrate with other systems, and providing that constant power means you can keep the batteries constantly charged. For lithium ion batteries, you can schedule running them down and bringing them back up. So that gives you a lot more control to manage the system and look after it than you normally would have. Our systems are extremely compact, and so there's the minimal impact for land. So farming is a big issue in this area. Land competition makes systems much more expensive, being much larger. And as you can see, Helios has the smallest footprint to produce renewable power and renewable energy. You can see in this size comparison, this is a 5 kilowatt system. Our 500 watt system, which is what we had here, only takes up about 1 square meter of space. So it's critically important. And what we propose with this system is that we can set up emergency stations at key points around the countryside for disasters such as this. The power can be used locally when it isn't being used for emergency. It can be maintained by the local villagers. We've done that and proven we can do that with this village and others we've worked with as well. These stations, again, can be expanded over time. So if we want to put more power in there, we can add more units. Depending on what the services are needed, power can be sent for up to 1.5 kilometers away from the unit. So even cell phone towers up on hills or critical infrastructure can be powered with just our 500 watt unit. That's all right. And the systems, can be integrated into larger commercial flows as well, which can be shown here. And so non-powered dams, industrial canals, used for water pumping and irrigation. So we can make larger systems for emergency stations as well that can produce 5-10 kilowatts or more, even up to 50 kilowatts. And we've actually been working with the Asian Development Bank demonstrating these larger units as well, the grant we received from them. So we appreciate that support greatly. And, finally, we believe that, this is one of the most impactful solutions on the market. We're addressing approximately 14 of the UN Sustainable Development Goals. This is something that we're really proud of, and we strive to achieve to help people all over the world, particularly those who are most in need. That is why we do this. All of us and our team have traveled all over the world. We don't go to the tropical resorts. We typically go to where the commercial sites are, and we've seen how everybody lives, and we really want to help, and that's why we're here. So in conclusion, and communication is one of the most critical requirements after a natural disaster, so that initially authorities and emergency responders can have vital information to direct resources most effectively. Following that, people can communicate with their loved ones to ensure that they are okay and provide help as they're available. Also, so that people in a disaster can get information themselves to know, what they're dealing with, so that they can make the best decisions for their survival and that of their neighbors, friends, and loved ones. With this, the reliable power, offers many other options that would now be possible, including, powering up a refrigeration system, with these, so that emergency supplies can be stocked, emergency medication, to assist during these times. When a typhoon's coming, you have some time to stock those things. They can be tracked. Powering local weather stations so you can get a really accurate on the ground information as to where things are happening. And, as we get going here, you potentially could charge a drone up and fly it to see the actual local area and get footage of what's happening. So all these resources and things come available. Even cleaning water with these systems can become available too, with now you have the power. So we believe that emergency stations utilizing the Helios power wheel should be distributed in ideal locations around the countryside and is the most effective way to support local populations, communicate and assist when resources are needed most. So thank you very much for your time.
Thank you, Michael. This is a really good presentation to set us off in this session, a really good start and very inspiring as well. And it shows the advantages of distributed renewable energy solutions in countries subject to extreme events, which is the case of the Philippines. And of course, ADB is delighted to be working with you on this mini-grid project in the Philippines. So we'll now move to our second speaker for today, who's Hansel Kubangbang, who's Senior Market Application Officer for Fluence in Southeast Asia. And he'll be talking about battery energy storage systems, grid flexibility asset of today, and really to understand how battery storage can be an important tool and technology for addressing climate resilience. He's the Senior Market Applications Officer at Fluence for Southeast Asia, and he has more than 10 years relevant experience in the Philippine electric power industry, with the focus on renewable energy and energy storage. Hansel, the floor is now yours. Thank you.
Thank you, David. Hello, everyone. First of all, I would just like to thank Asian Development Bank and the organizer of this event for allowing me to share my insights about the critical role of battery-based energy storage system in the clean energy transition. So let me start with a brief introduction of Fluence. Fluence is a technology and solutions provider. We have more than 4,800 megawatts of installation in the world across 30 territories and countries. We started in 2008 by installing the first BESS in PJM interconnection for frequency regulation. We continued to be the global leader by installing the fastest battery-based energy storage system in the world in Ireland. And then also in 2020, we started delivering the largest battery-based energy storage system portfolio in Southeast Asia of around more than 500 megawatts across 20 sites in the Philippines. We understand the value of energy storage across all segments of the energy industry. We focus primarily on 8 main applications of energy storage. And from that, we have developed more than 40 applications, all customized according to the need of the grid, of the country, and of the customer. But some may not be ready adopting such technology. Some may say that their frequency is okay, they can address the challenge of renewable energy integration. But we've seen several countries adopt energy storage to address these challenges. Some are confident that their existing power plants can address these challenges, grid flexibility, frequency regulation. But this may be true now, but that may not hold in the future. A comprehensive study will show that energy storage is the most cost-effective solution and a more climate-resilient solution. Grid operators, regulators, and policymakers often face the same challenge, the ancillary services trilemma. We all want an affordable, capable provider that is available all the time. And we know that hydro, thermal, traditional resources may not be the best option. Battery-based energy storage system has been proven to provide the fastest response with 95% availability factor at a reasonable price. Battery-based energy storage system is a cost-effective solution because it provides a faster response and it provides higher megawatt response as compared to traditional sources of frequency regulation like hydro and gas turbines. Battery-based energy storage system is not affected by season. As you can see in this graph, hydropower plants is very limited during the dry season, El Nino and La Nina, especially in the months of April, May, and June in the Philippines. And it is a big challenge for systems who heavily rely on hydros for grid flexibility and frequency regulation, like the Philippines. And with this, some say that energy storage provides a more climate resilient solution than traditional resources. As we see more and more renewable energy integration, we should expect that the net load profile of the system will change. Hence, a stronger demand for peaking capacity and the need for grid flexibility. And that is why we see this steady increase in terms of energy installation in the world. They already have realized the value of energy storage in the clean energy transition. Germany, USA, UK, Philippines, Taiwan, and Australia, and many more have already installed energy storage. And in fact, they have made energy storage as part of their clean energy transition roadmap. Energy storage has been proven to be a cost-effective, a more climate-resilient solution in enabling renewable energy integration. Developers, investors, IPPs are just waiting for the right market signals. This may include policy, framework, or tariff structure for energy storage. And we Influence, we're here to support the best that we can. So together, let's transform the way we power the world to create a more sustainable future. Thank you very much, and I look forward to your questions.
Thank you, Hanzo. I think that was great and a nice sort of segue from Michael's presentation, where you can see that there's synergies between renewable energy and battery storage and helping that the system become more resilient as well, even if there's seasonal differences. So this is really good. With that, we will move to our third speaker for today, who's Tsuyoshi Shiga. He's the manager of International Business Promotion section at Asano Taisei Shikizo Engineering, and he'll be taking us through some of his work on using waste heat or waste cooling, let's say, from industrial wastewater in Vietnam. He has almost 30 years of experience in environmental projects and is currently based in Vietnam, working on innovative technologies across different water-related sectors. Tsuyoshi, the floor is now yours. Thank you.
Thank you, David. And I'm Tsuyoshi Shiga from Asano Taisei Engineering, ATK Japan. It's an honor to be here to give you my presentation on my project today. This is a project funded by TIC, Technology Innovation Challenge, by ADB, and it was started May 2021 until the end of this month. The energy consumption is growing up rapidly as the economy is booming in Vietnam. Meantime, plenty of energy are forgotten or ignored in the manufacturing process in many industries. A chicken processing factory in Vietnam uses and release very cold water. My project is trying to utilize the discarded coldness for energy saving and the CO2 reduction of the factory. I'm glad to share the knowledge and lesson learned through the project with you today. And the heat exchanger of the system called GHEX, this one, is made of polyethylene, which is strong against corrosion or rust. Metal type heat exchanger have dominated the market because of the advantage of the material property, especially thermal conduction. Also, the polyethylene is lower thermal conductivity than the metal material. The unique shape of GHEX, combination of more than 100 small pipes compensates the weakness of the polyethylene made system. In this project, 3 units of roll-up type was installed in a water tank. The chicken processing factory uses very cold water, 0 degrees Celsius, for their production. The cold water is made from industrial water, 30 degrees Celsius, and by electric chiller. And also the wasted water is still very cold, that is 2 to 3 degrees Celsius. And the coldness is now discarded. This heat exchange system utilizes the coldness for cooling the industrial water by 5 to 7 degrees. And this is called pre-cool system, and useful to reduce energy cost and CO2 emission from the factory. After survey and design work, some of the core equipment was delivered from Japan, and the system was installed in early December last year. And the commissioning and operation was studied, and it was working until now. For evaluation of the system performance, key factors such as water temperatures and flow rate were closely monitored. The data indicates that the actual temperature and flow rate are slightly different from the preliminary survey result. For example, the black text values are gained in the preliminary survey, and the red text values in the slide show the data as of 17th December last year, just after the start of the main operation. The temperature of the industrial water is 23.86 degrees and not 30, and 6 degrees lower than expected. And the cold wasted water temperature is actually 3 degrees, 1 degree higher than expected. And the flow rate of the cold wasted water is 95 liters per minute, and the industrial water is 78.8 liters per minute. So almost triple or double than expected. Based on those monitoring data, the performance of the system is calculated. And the required factors are the temperature of the industrial water and for inlet and outlet, named T in and T out, and the flow rate of the industrial water F. And this is a picture of the installed system. This was installed in basement of the factory. Only 10 meter length and 3 meter wide is required for the installation. And the cold wasted water comes into the treatment tank from the wasted water pipeline. And the water goes into the main heat exchange tank here. And the circulated water inside the GHEX is cooled down. And the cooled water goes into the plate heat exchanger here. And in this plate heat exchanger, the industrial water is cooled down. That is the principle of the system. And the factory consumed 615,000 megawatt of electricity, or 45,000 US dollars annually, only for producing the 0 degree Celsius very cold water by the existing electric chiller. Those value is 20% lowered if the GHEX breakthrough system is fully applied, and then resulting 110,000 megawatt or 9,000 US dollars, or 100 tons of CO2 is saved annually. The initial cost of the breakthrough system is 59,000 US dollars in this project. Therefore, the payback time is 6.6 years. As this project is a trial study, we used many monitoring devices for the system evaluation. However, in the commercial use, those full spec monitoring devices and some electric work are neglectable. So considering those cost cuts, the payback time can be shortened until 5.3 years. The proposed system can be applied even for a hot condition until 80 degrees Celsius. And the factory is also using 80 degree hot water in their production process and releasing hot wasted water that is 60 degree without using the summer energy. Therefore, hot system can be also beneficial to reduce the fuel cost for an existing boiler in the factory. And moreover, the cold wasted water discharged from the breakthrough system is still cold. That is 10 degrees Celsius. So this coldness can be used for room cooling as a water type heat pump system. And those combination of pre-cool and preheat and the room cooling system will be proposed to the factory in the next step. As the water quality is different between the cold water and the hot water, different obstacles such as requirement for different preliminary treatment will be the possible challenge for a better application in the future. And the cold and hot water commonly used in many industries such as fishery or textile. The cold water is used to wash shrimp or fish fillet, and then dirty water after dyeing process in the textile production may be other potential field to apply in the future. Thank you very much for your attention.
Thank you, Tsuyoshi. This is a really interesting presentation, and we wanted to highlight with this presentation that, of course, we understand there's an increasing demand for cooling across many countries in Asia, and just to show that innovative technologies, as shown, can help us use existing waste resources for productive use, and in this case for cooling and as well as heating. And so we really wanted to bring this to everyone's attention. With that, it concludes the presentations that we have and sort of set the scene on technology applications to support climate resilience. And we'll now move to the panel discussion and invite the three previous speakers to join us there. To start, I would like to introduce our first panelist, Kim Shi-dang, who's a project officer from GIZ's Climate Resilient Economic Development. And she has over 16 years experience in environmental policies and standards, sustainable development and green growth, and climate risk and vulnerability assessments and climate adaptation. Although she's based in Vietnam, we'll ask her to talk about GIZ's work in Kazakhstan on enhancing energy system resilience to climate change through macroeconomic modeling, as well as her work in Vietnam. Shi, the floor is yours. Thank you. Can you tell us a bit about the work you're doing in Kazakhstan, and also what are the policy recommendations and findings from your study, and how would these be relevant for other countries such as Vietnam? Thank you.
Thank you, David, for your nice introductions. And firstly, I would like to also thank you, IDB, and the organization of the ACEPT 2022 Forum for your invitation to be a panelist in the ACEPT Forum today. And as Davis has introduced, my name is Chi Dang, and the project officers of Climate Resilient Economic Development Program based in Vietnam. Our policy advice for Climate Resilient Economic Development Program is commissioned by German Federal Ministry for the Environment, Nature Conservation and Nuclear Safety, so-called BMU, and implemented by GIZ in 3 countries, in Georgia, Kazakhstan, and Vietnam, from 2019 until the beginning of 2023. In the 3 countries, we use the macroeconomic models approach to simulate the impacts of climate change and assess the effectiveness of adaptation interventions. The aim of the project is to give evidence-based policy advices to the adaptation planning processes in Georgia, Kazakhstan, and Vietnam. And so far, we have gained some achievements in mainstreaming macroeconomic modeling into policy advising. Within the time limitation of today's section, I would like to share with you the experience that we have in Kazakhstan and Vietnam, and probably leave Georgia for the next time. Firstly, about Kazakhstan, the CREAT project in Kazakhstan has been supporting some policy processes, such as the low emission development strategies. As you may know, Kazakhstan pledged to achieve carbon neutrality by 2016. And the least cost decarbonization pathway model by the Ministry of Ecology, Geology and Natural Resources, with support from GIZ Green Economy Project. The so-called LEDS hybrid model has been elaborated to support the modeling preparation for the least cost decarbonization pathways. And the soft linkage with the CREAT modeling results has been mentioned in the LEDS documents. The last chapter on adaptation is under elaboration with support from CREAT to ensure a holistic approach towards low carbon and climate resilient economic development. And secondly, CREAT project in Kazakhstan has support NDC roadmap on adaptation. Kazakhstan NDC is complemented with the previous missing part on adaptation, and the preparation of the adaptation in the NDC has been supported by UNDP and led by the Ministry of Ecology, Geology and Natural Resources. So in the last couple of years, CREAT modeling results has been integrated to NDC roadmap on adaptation, and CREAT approach recommended as an additional tool to evaluate adaptation options. And thirdly, CREAT Kazakhstan has support the UNFCCC National Communication Report. Presentation of the CREAT modeling results for integration to Kazakhstan National Communication Reports has been delivered a couple of months ago. And next, I would like to also highlight some progress with the policy support in Vietnam. CRED in Vietnam has support to elaborate the adaptations actions in the national strategies and action plans. Vietnam has pledged to achieve net zero emissions by 2050 in the COP26, and the COP26 implementation program led by the Ministry of Environment and Natural Resources. Currently, the updated NDC and NAP are being also led by MONRE, the Ministry of Environment and Natural Resources. At the national level, we also have other strategies and actions plan, plans going on, such as the Vietnam Green Growth Strategies and Action Plan, led by the Ministry of Planning and Investment, or MPI, with support from the GIZ Macro Green Growth Project and the CRED project. And the soft linkage with CRED modeling results in the Vietnam Green Growth Strategy and the National Action Plans has been mentioned in the preparations and technical documents of the strategy and the action plan. The adaptations interventions and has not been modeled in NDC and NEF, and we see that is a gap for the support needed from the CRED modeling approach in Vietnam. Also currently we has been supporting net zero emission roadmap. The roadmap is led by the Ministry of Planning and Investment and under preparation until the first quarter of 2023. With support from also the GIZ Macro Green Growth Project and CRED project in Vietnam. The adaptation chapter is under elaboration with support from CRED to emphasize adaptation and mitigation interlinkage with the balance of resource mobilization to achieve the net zero emission goal. And the DG-CRED approach will be recommended as an additional tool to evaluate the investment needs on adaptation, particularly to sectors like agriculture and forestry, which are most vulnerable to climate change, and some other sectors like sea dye system, road system, houses, and urban drainage system, and potentially the energy system as well. In the next phase, the DG-CRED model can be extended to also incorporate a mitigation block, and the aim is to model a holistic approach of green, inclusive, and resilient economic development pathway as stated by the government. Thank you so much for your listening and attention.
Thank you, Shi, and thanks for your points. I think it's really interesting. I think it's important that we have policy support for climate adaptation. As many of you know, climate adaptation financing is still below what is really needed, and as we're heading for beyond a 1.5 degree, it's becoming ever more important, and I think projects like yours are really important to get the countries in shape, to get them to develop their strategies, to get them to develop their national adaptation plans if they don't have it in place, and then help us understand where financing is needed. So this is really important. Maybe to highlight, Shi, that the work that's been done by GIZ in Kazakhstan is available online, and it's very comprehensive, and I had a look in terms of the data information there is very useful for anybody that's looking at climate adaptation in in Kazakhstan, and hopefully the work in Vietnam will be available soon. So this is a nice segue also to the next panelist, and I'd like to introduce you Catherine Lamers, who's research at Rainier Lemoyne Institute in Germany. And it's quite early at her time, and I'd really like to thank her for joining us. And her PhD research, she looked at electricity access and climate change impacts on Southeast Asia. And currently she's involved in demand estimation and energy system modeling for health facilities as well in the region. She's worked for 2.5 years for GIZ in Bangkok and managing an island electrification project and supporting provincial energy planning. So a lot of synergies with many of the speakers here. So this is really great. So Catherine, I've got a couple of questions to get us started. So can you tell us a bit more about your work and the importance of climate resilience for island communities in Southeast Asia? And what have been the findings of your study in terms of adaptation measures to mitigate climate risks through better planning? So the floor is yours, Catherine. Thank you.
Thank you, David. Yeah, usually I'm not an early bird, but yeah, thanks to the fellow panelists as well for their inspiring presentation and talks. And I totally agree to David that my research actually connects to many of the aspects that were already mentioned. I'm actually very grateful to be able to present the research that I've been doing over the past 3.5 years at this year's Asian Clean Energy Forum. But before I take you to the journey of the highlights of my PhD work, I want to say a few words about the institute I'm working for, the Rainer Limon Institute. So that's the research institute where I actually did my PhD research that is finishing off at the moment. And I'm continuing to work with them as a researcher. And we are a research institute situated in Berlin. That's why it's quite early for me today. And we are actually doing applied research for 100% renewable world, so it's quite ambitious. And we do have 3 different research units. So we actually do research about renewable energy-based mobility, but also we have one unit that is actually looking at large centralized systems and how to integrate higher renewable energy shares into that energy system. And I'm actually with the off-grid systems team. So we have a lot of different projects in, for example, Southeast Asia or some African countries. So we look more into electrification strategies, developing those, and doing more the modeling of the decentralized smaller systems. And as David said already before starting at RLI, I've been working with GIZ for 2.5 years in Bangkok. And there actually the motivation started to do my PhD research as well, because there I was involved in an island electrification project where I have seen some energy infrastructure that was actually destroyed by storms and hail. And I felt as well that while working with the island communities, that they are already quite concerned about climate change, about the impacts on the islands, and that they really feel that they need support and that they need to adapt to the changing conditions. And then I was like researching more on what is actually a key enabler for adaptation measures. And I actually found out that energy access is one of the key enablers. I mean, it connects to many of the different sectors. It connects to agriculture, so it can support water irrigation and pumping, or as Michael mentioned, it can actually enable water purification and so on. And especially in an island context, it really helps to increase the independence from the mainland. That is a crucial factor for many of the islands, because they have actually, because of climate change as well, more days where they actually can't travel to the mainland because of rising waves or storms and so on. So I think for them, it's really important to have this independence as well. And especially while we are talking about Southeast Asia, this is crucial because this is one of the regions that is most threatened by the impacts of climate change. And I also found out that many of the people that are still lacking access to electricity in Southeast Asia are actually situated on the remote islands in the area. So it's kind of particularly important for the island communities to get reliable energy access, and as well to then increase their resilience as well. So it's kind of a win-win situation to get access to electricity, and then they are actually enabled as well to increase their overall energy resilience. And in my research, I was more focusing on then the technical adaptation measures. That is, the reason behind it is that it's nice to have electricity access, but this electricity access has to be resilient itself as well. So it doesn't really help the communities if it's like blown away with the next cyclone or storm, or if it's really affected by rising sea levels. So we really need to focus on climate resilience for this remote island communities and their energy systems as well. And what I actually found out in my research, or what I did, is first of all to do a climate change risk assessment for all of the islands in Southeast Asia. So I really looked into the details of each island, what kind of impacts are actually there, and to detect certain risk patterns as well in the region. And I identified mainly 4 different climate change risks or impacts that are actually affecting energy systems, which is the temperature increase, precipitation fluctuation that can be either droughts or floods, extreme weather events like typhoons and cyclones. And then speaking of an island context, obviously sea level rise is an issue as well. And all of these 4 different impacts are actually affecting different parts of the energy system. So it's not only affecting, for example, if a cyclone is blowing over an island, so it's affecting the technical components directly. So, for example, there's damage to the solar system because it's blown away, but it's also affecting the output and efficiency of the system. So with rising temperatures, for example, you observe a decrease in efficiency of the different components. And then it's actually affecting the loads to be supplied and the future demand as well. So we see there an increase in demand because there's an increase in cooling demand. So it's really like a big matrix what I had to keep in mind. And coming back then to this island-specific risk assessment, so I actually found out that for all of the islands, we observe a temperature increase. It's roughly between 1 degree and 1.5 degrees. I took the RCP, the representative concentration pathway 4.5 into consideration. So if it's the intermediate scenario, so it will probably be more. And what I found quite interesting in my assessment is that for most of the islands, we actually see a flood risk instead of a drought risk, and it's actually a slight to a high flood risk as well for a lot of islands. And they're actually facing few up to 267 cyclones within 50 years. So that's quite significant, and that's quite significant for the energy system planning as well. And talking about the sea level rise, so here I observed that some islands are not struggling that much with sea level rise, but some are actually losing up to 100% of their land over the next 30 years. So this is quite dramatic as well for the communities, obviously, and it comes with a certain challenge for energy system planning as well. In terms of the risk patterns in the area, so this is really dependent on either the geographical location of the island. So we have heard about the Philippines, for example, where frequent typhoons and cyclones are hitting. So this is actually in line with one of the global cyclone hotspot areas. So there, the geographical location of the islands plays a big role if they are hit frequently by strong storms. And other risks are actually more related to the island characteristics, like size or topography as well. So if the topography is very flat, then they're actually losing a higher proportion of their land. And then actually in the second block of my research, I was more then connecting the climate change impact to the energy system planning part. And I had the challenge that there's actually a lot of data on large centralized systems, but there's a lack of data for decentralized systems. So what I did is that I actually went for expert interviews. So I interviewed 22 experts in the region, being it island communities, implementers, policymakers, insurance companies, to find out a bit more about like suitable adaptation measures, and as well how to integrate it best into the energy system planning procedure. And here I actually came up with a list of very different adaptation measures for all of the risk I was looking at. It's a huge variety of measures, like simply strengthening the mounting structures, for example, or making the systems removable. So that's why I found the aspect that Michael mentioned quite interesting as well, that the systems are actually portable or can be removed in case of a disaster. But they did not only touch the technical adaptation measures, but they also highlighted that an enabling policy framework and institutional framework is actually very helpful. That connects nicely to what Chi just presented. And it's as well very important in an island context with this remote communities to keep like the social aspect in mind as well, and to consider like the power dynamics on the island as well. And in terms of the extra investment costs, so I linked all the different energy system components to kind of what does it actually cost to make them resilient towards the different impacts of climate change. And here it was a very broad range of kind of extra investment cost to adapt the different components, and it was actually between 2 and 22%. The highest additional investment cost the interviewees saw was actually for the grid infrastructure, and to protect the grid infrastructure against cyclones, against strong storms. For the hydro power generation, for example, just to give you some highlights, the highest investment cost would probably to protect them against like strong floods. And this is the same for the solar generation. And sea level rise actually had the lowest impact, let's say, according to the interviewees. And how I actually integrated these findings into energy system planning is that I took actually this extra investment cost and modeled business as usual planning, energy planning, and then integrated to climate resilient scenarios. So where I took, first of all risks that are actually applying, and then took the extra investment cost that are actually needed to protect the energy infrastructure against the impacts of climate change. And then I had one climate resilient scenario where I only looked at the most urgent or highest climate risk actually. And what I found quite interesting is that the difference so I did more an economic evaluation of it, and that the differences in the cost of electricity are actually not that high. They are highly dependent on the setup on the island. So the smaller the island, the lower the demand, the higher the costs are, and the higher are actually the difference in cost between like business as usual planning and then climate resilient planning. But I actually had 2 case study islands where the difference was only like 3 cents per kilowatt hour if you compare then the business as usual and the climate resilient energy planning. So this was quite interesting to see for me. And then I, like at the end of my research, I was then evaluating the business as usual planning and the climate resilient energy system planning over the project duration of 25 years, and so to say simulated damages that will happen to the business as usual system setup. So I applied different frequency of damages, 5, 10, and 15 years, and as well different percentages of the damage, like how, like it was the system completely destroyed or only half of it or a fourth of it. And there I actually found out that over the long run, and that's something that David mentioned in his introduction to the session as well, so I can confirm this, over the long run, resilient energy planning actually makes sense for most of the cases. It's again very island specific. You have to really look at the different at the demand and how many, like what kind of energy infrastructure you have, what kind of climate risk are applying. But for most of the cases, I would say like 80% of the cases, it was really worth to go for resilient energy system planning. All right, so to come back to the initial question, I think, yeah, so adaptation, like climate resilient, is very, very important, and adaptation is very important for the island communities. While working with them, I really felt it, that they are worried about it and that they are keen to learn more on this. And adaptation measures, there are plenty available, plenty of ideas, and they are really specific to the risks they are actually address and to the component as well. And with that, I want to end my talk, and I'm really looking forward to the panel discussion and the questions.
Thank you, Catherine, and it's a really great segue for the discussions. Now we've got about 15 minutes left, so we'll invite all the panelists to join, and just to touch upon some of the things you said that I found really interesting. Of course, as mentioning energy access as an adaptation measure itself, of course, to allowing resilience of communities, and I think that'd be great. I think a lot of people would be very interested in your work. So if you could let us know when it's available, or if it's available, where we can find it. I think many of the colleagues, the speakers here, will also be interested. I'm sure Michael would be happy to share some data as well to support your study and future work as well. And I think the other thing that I take from what you mentioned is it's, of course, when you're structuring and preparing these technologies and projects, you can't look at them in isolation. You have to look at the surroundings, and of course you're planning for what's happening today, but the situation in 10, 20 years might be very different, unfortunately, and there might be more typhoons, there might be other kind of things that you need to plan to. So how can we develop these projects so that they're adapted not only for what's happening today, but into the future? And maybe just very briefly, I'd like to ask Michael to sort of comment on what sort of you mentioned very briefly, but also I think touch upon sort of how significant he sees the micro hydro as a renewable energy resource in the future to address climate resilience. And then we have a few questions from the audience that maybe we'll ask you, Michael, before we pass on to Hensel and to Tsuyoshi as well with some follow-up questions. Thank you. Michael.
Yeah, so we think it's I guess extremely important for future climate resilience. Integrating these systems, and particularly the areas obviously where we're going to have the most impact. You got to have the right technology for the right area. So in the deserts and places like that, solar is going to do much better than we are, and probably wind. But in tropical regions and places with higher rainfall, that's where that's our sweet spot. That's where we can really outcompete other technologies and be really impactful. And one of the things with our really small footprint is that with a lot of these other renewable technologies, one of the downsides is you have to clear a lot of land. And in a lot of these tropical places, that's where tropical rainforests are and things. And so with the really small footprint, like you literally don't need to cut down a single tree to put one of our units in to produce power in those areas. So I think that's also part of the resiliency in the environment that we talked about. and two, that reliable, consistent power. Pairing with batteries like Fluence does is going to be really critical for these intermittent power sources, because as we get further and further away from other hydrocarbon sources, that is the big challenge. And charging those batteries and having that backup power, which is sort of a sunk cost in a lot of ways on grids that isn't counted toward what we're doing, that sort of other technologies get the benefit of, in terms of their overall costing, that sort of isn't taken into account for what we're doing when that's not required. So, yeah.
Thanks, Michael. Maybe just we have you, and before I maybe ask some questions to Hansel, I think we had some questions from the audience in terms of sort of what's your plans for the future in Southeast Asia. So I think some people are interested to see how they can look at your technology. And the other one is sort of understanding the typical costs of installation. And of course, sort of linking it again to one question where people are asking, so how do you integrate it with other technologies such as battery and solar? And so, of course, the project that you're working with ADB in the Philippines, and maybe you can talk a bit about that just for 1 or 2 minutes.
All right.
Thank you.
Let's get through. So first, we are definitely working in other areas of Southeast Asia. We have wheels actually on the way to Borneo right now. One's for a remote village farm area, and the other is going to be for a local rural school. And we're definitely interested in talking to people about projects in other parts of the regions. We have units available and ready to go and ship. So our manufacturing partner is supplying those and has those ready to go for us. I think the other question was on sort of the pricing. Right now and kind of where we're going, if you can imagine sort of solar at scale, has gotten down to extremely low prices, and we're just starting out. So we're just ramping up and trying to get to scale. But with that, even on very low number of units, we're actually lower price than solar at scale for off-grid power because it's a consistent, reliable power. And so and with that as well, our price per kilowatt is going to be higher. We produce 3 times the power as a similarly rated system, kind of in the worst case scenario. In some places, we produce up to 5 times the power. So if you're looking at a 5 kilowatt generator, you're looking at something that's going to be in the range of around $40,000 today. As we get to scale, I think we can bring that down closer to around $20,000, which is pretty close to what you're looking at for a 5 kilowatt system now for solar. So that's where we see the future and where it's heading for that size. And what was the other part? I think there was one more part to the question.
I think maybe the thing I would also like to link it into what Katrin was mentioning in terms of, so of course you're building the systems to withstand the current situation, but of course Philippines might have more frequent floods and typhoons. So how do you look at in the area? So you were saying that a lot of debris happening. How do you work with the community so that ensuring that if this is happening every so often, that the debris is not impacting, and that any landslides and so on might be impacting this essential project, which for that community? I think that'd be good to take us through.
Yeah, I mean, obviously, definitely siting the units for landslides and things like that. You want to avoid those. Where you can, divert the water through a side chute canal, you can avoid a lot of the debris that way. Although they'll do some that kind of minimizes the extremely large debris that comes down large rivers, but we would, you can divert water for smaller units. We do have designs where you can put the larger units in larger rivers, where we can actually set posts that are high enough that we can raise that unit up so we're above the predicted flood level, and so the debris will normally pass through and below the unit and around it. So we kind of get designs where when the water does come up that high, it will flow over and around the unit, but when the water's lower, it's directed through the unit. So we've got designs around that for those kinds of situations. I think the other part too from before is integrating with other technologies. And so we've done that with villages already and with batteries. One of the things that actually we are extremely compatible with solar on and the batteries is we work with the same types of systems and inverters and things. So we can actually have the cost of the inverters and power takeoff system on our wheel, and then you plug in solar on top of that and add it, and you don't need to add those power electronics. So those costs are shared actually between the generation systems, which lowers the overall cost of the power of the project. So and that's how we do that. And again, obviously integrating and connecting the batteries into that is pretty straightforward. So. Yeah.
Thank you. And that's a good segue to ask some questions to Hansel on battery storage. And I think it'd be great, Hansel, if you could sort of tell us why you think these energy source storage systems can be important for enabling renewable energy integration, particularly in small island communities, to link to sort of the work Michael and Catherine and others have been doing, and really understanding how energy source storage systems can enable climate resilient services. So if you can talk a bit about those linkages and maybe some experience you've seen where the grids have been impacted by extreme events or floods or droughts, and how battery storage systems have helped that'd be great. Thank you, Hans.
Thank you, David. Yes, energy storage systems, especially battery-based energy storage systems, are really, really important in this green energy transition. We have seen, this is in actual, that by introducing more flexibility to the grid, energy storage can help integrate more solar, wind, and other distributed energy resources. Energy storage can also improve the efficiency of the grid and existing power plants by increasing their capacity factors and offset the need for building new polluting emission peaking plants like fossil fuels. Yeah, and in terms of climate resiliency, in the Philippines, we have 3 major islands, right? Luzon, Visayas, and Mindanao. Luzon and Mindanao is very rich in hydro. Visayas doesn't have hydros. They have but very, very minimal. And in the Philippines, hydros are the main providers for frequency regulation. So imagine Visayas, they have lots of solar, but they don't have frequency regulation because they don't have hydros. But we were able to install several battery energy storage systems in Visayas, and that helped the grid operator manage the intermittency, the variability of the solar in the area. And during extreme events wherein certain island will be disconnected, for example, Negros, the ever famous Negros Island, when Negros will be disconnected from the main grid, since the battery energy storage system is in there to regulate the frequency, so it can really withstand such islanding. And then, that's one of the best benefit that battery energy storage system can provide.
Thank you, Hansel. And just a follow-up question, although you can't tell us sort of prices of the battery storage systems, but could you let us know what are the key elements that will determine the cost of the system? So what is it the application that it's being used to? Yeah. Of course, the size. So people, of course, can understand sort of how the prices will change according to the system integration and how it's developed. Of course, each situation is different, but it'd be great to talk a bit about that. Thank you.
Yeah, cost is always the most difficult question. So, I mean, for battery-based energy storage system, it really depends on the use case. Will it be used for frequency regulation, for energy arbitrage, for voltage regulation? Utilization, will it be used frequently every hour for 5 years, 24/7? Or will it be used during peak period? So those informations we have to gather, we have to understand for us to be able to provide a realistic cost for that project. And we can support the customer, build the business case, and help them achieve an attractive return. And we've done the same in Southeast Asia and Asia Pacific region, in the Philippines, Taiwan, India, and Australia. That's why, we're now delivering more than 1 gigawatt hour of battery, because we have supported the customer. We have shown them that the business case works, and this is the return for each of the application, for each of the country. And we can do the same in other parts of the Southeast Asian region.
Thank you, Hansel. And maybe just one final, how small are the battery systems that Fluence can do? So in terms of size, what's the smallest size you can do, just for our audience as well?
Right now, we are mainly focused on grid connected or grid utility scale energy storage. I think the smallest one that we have is a 2 megawatt energy storage system in Taiwan. Our largest is a 300 megawatt 4-hour system. And right now, I think we're working on a larger type of energy storage system. But we're kind of keeping our eyes open in the segment of, say, for example, kilowatts, because we know that in the future, distributed energy system will be the next big thing. Because that's why we're keeping our eyes open in that segment. But right now, we're more focused on grid utility scale because of price, utility scale.
Yeah, thanks, Anton. Of course, utility scale is also important. If the grid is down, and supporting these islands, as you're giving an example of the Philippines, and ensuring that these are on even after a storm or extreme events. So that's great.
And we are working on several projects now for behind the meter application as well, for industrial use, like cement plants, food manufacturing companies, especially in the Philippines.
Thank you. So that's also keeping the industry on and running. So that's very important. A couple of questions maybe to Tsuyoshi as well, just and then I think we've got about another 10 minutes for Q&A, and there's some questions for Catherine and Shi that I'll be asking very soon. But maybe to Tsuyoshi, just to expand a bit about your presentation, where do you see other opportunities and different sectors where your technology can be applied in developing countries, and what's the sort of key factors that you see for successfully disseminating this and other innovative technologies so that they're used more widely, and any lessons learned you have from implementation of the project that you've been doing in Vietnam, and how that can support future development. I think that's important particularly for new technologies. I think maybe also with Michael, when you're starting, sort of lessons learned. So maybe Tsuyoshi, onto you, these three questions. Thank you.
Thank you very much, David. And I think one of the promising opportunities to disseminate the technology in the DMC is, I think, fishery industries, as shown in my slide, and especially the onshore aqua farming is becoming very popular in the world, and I think the climate change is bringing the extreme weather, damaging the offshore farming system. So it needs onshore aqua farming need to control the water quality and temperatures and all the time. So I think my system will help to control the system properly, and that is probably one of the promising opportunities for the technologies. And I think the key factors to disseminate the technology in the other countries is governmental policy on energy saving, and most of the Asian countries, ASEAN regions, forecast the increase of the energy demand for the next decades, and governmental support such as subsidy for the initial cost or tax exemption for the environmental friendly technologies will be the key factor for wider application in domestic countries. And the other factor is cost reduction of the system. As shown in the slide, the 6 to 5 years we will need it for payback time. And so the production cost of GHEX system, the core system, is a big challenge. And I think the mass production of the core system in ASEAN region can be the answer for future dissemination. And lesson learned from the project is I think that the system was designed to turn on when the cold wasted water comes in the pre-treatment tank. And however, the industrial water was not always supplied into the system. It depends on the factory's operation status. And I think that those kind of fluctuation will occur in other countries, other developing countries. So the optimization of the control or operation of the system will be probably the most important, one of the most important factors for the future application. That's all.
Thank you to Tsuyoshi. That's really good to sort of learn through the experience. And I think one thing I'd like to touch upon is that you mentioned about policy support, and I think that again links to well with Shi's work at GIZ. And here I'd like to ask Shi, can you tell us a bit about how GIZ is expanding its work? So you touched upon the work in Vietnam and Kazakhstan, and policy support is so important. Can you tell us a bit about what GIZ is doing in other countries through this program or others in terms of supporting countries with climate resilience and climate adaptation in the energy systems? Thank you.
Thank you, David, for your question. So even though that I'm representing CREATE, a global program of GIZ today, but you know that my experience is mostly attached with Vietnam. So I would like to share with you some information about how the resilience of the energy sector is you know, integrated into the policy preparation processes in Vietnam. And so both the NDCs and the National Adaptation Plan and the Green Growth Action strategies, plans, and action plans of the green growth already mentioned the importance of adaptation and resilience to all economic sectors in Vietnam. And also energy sector is one of the particular sector that they would also highlight in the documentations of the strategies and plans. But actually in Vietnam, we still are lacking of the technical supports and the financial resources to do, you know, deeper research on the resilience of the energy sector. So most of the current research is focused on the resilience of the hydropower, but not the whole energy sector. So somehow we think that it is the area that when we can further you know, develop in the future. Thank you.
Thank you, Shi. That's and it seems like there's a lot of interest in the hydropower, and,
That's
and
right.
Of course it is an essential technology, and we'll need more of that at smaller scale and larger scale as well, and a combination of different technologies. So it's very important. We just got a couple of minutes. I've got one last question for Catherine. So Catherine, you've got about 2-3 minutes to cover this question from the audience, which I don't find an easy one, but hopefully you can help me in terms of looking at the social, cultural aspects to be considered in deploying climate adaptation measures, and sort of the kind of scenarios you looked at, and sort of what's the lessons learned, and is it easy to standardize this, and there's like one solution to address this, or you have to look at adapting it across different islands, different cultural situations? So that's how I sort of understand the question. But Catherine, on to you. Thank you.
Yeah, thank you so much as well for the question. To cut it short, I would say the one fits it all, one size fits it all. I think it's not really applicable from what I've seen and what I've learned. Maybe to add on what I've mentioned earlier, so I did apply my approach to 3 different case study islands, and these were having a different risk profile and different sizes of the communities. It was from like 80 households to 200 households, and then one island actually just having a temple and a camping ground. So they were really different, and the results were different as well. So I would really think that it's like specific to the island context. Let's say, for example, the specific climate change risks that are actually dominant on the islands. And then obviously it depends as well on the renewable energy source that is available. So there I would say, like, it's difficult to do a one size fits it all solution. And in terms as well on like adaptation measures and energy access as well. So I would say it already starts with asking the community if they want to have access to electricity, because I mean, on some islands, they're afraid of it as well. So, I mean, there it needs a dialogue as well. So I guess it's always backstopping with the community, assessing their needs first, and then implement measures as well. I mean, it's a variety of measures that you can actually implement, but it always depends on the specific community and as well their power dynamics. And actually, on a sidetrack of my research, I was looking at the triangle of climate change, energy access, and gender equality as well. So there I found out that like it's actually crucial to involve women in all of the development, like being at the coordination, being at the first dialogue, or then implementing and planning the energy system. So if women are involved, the systems and the implementation are prone to be more successful as well. So here, I think the social and cultural aspects are really important as well. So just to point that out as well on a final note. In my research, I only focused mainly on the technical aspects, but I would have loved to investigate more on the social and cultural aspects as well. Thank you.
Thank you, Katrin. So that's a nice segue to further research in this area. But I think the last point you made, I think, is very important in terms of course, we've got to look at policy support. We've got to look at the technologies, which we covered here, but maybe we didn't touch much upon, but a very important part is about communication and awareness. And that's a really essential part for most of the work we're doing. And so really I would like to thank all the speakers today. Based on the discussion, it shows it's really important to look at assessing climate change risks and impacts, adopting climate resilience and adaptation as part of government policies and regulations, and the third, maybe implementing and investing in climate resilient measures, and it does pay off in the future, as we saw, and this is an area where ADB is working quite hard with many of you here, with Michael and Tsuyoshi particularly doing some projects, and very glad to do so. So with that, I would like to sincerely thank again our speakers for their time availability, some very late in the evening, some very early morning. We hope you found the session interesting and have a clearer picture on how to develop more resilient energy systems in your day-to-day work. So this concludes the session for today, as well as our thematic track for the Asia Clean Energy Forum. Please do join us tomorrow for the remaining sessions, as well as the closing plenary. We look forward to receiving you at the Asian Clean Energy Forum next year. Hopefully we can do it in person, and hopefully we can meet many of you in person again. So thank you for your attention, and stay safe and well. Thank you.
Thank you,
Thank
David.
you.
Thank you, everyone.
Thank you, David.